Thank you. Thank you for any introduction. And well, the pleasure is mine. It's a shared pleasure, let's say. Um, so, as we have probably a worldwide audience, I will say good morning, good afternoon, good evening, so that, to make sure that everybody is greeted correctly. And well, I'm going to talk about sensing technologies, and it will be more like experience sharing with two type of technologies. One is optical fiber sensing, and the other one is wireless sensing using MEMS, so electronic microsystem. And let's say I will start the presentation by a quick introduction, giving you some motivation for why we do that. We will then see some details about optical fiber sensing. So I will enter into the physical principle of that type of technology, and optical fiber technology is multiple. You have many type of sensors. So I'll be focusing only on what we call distributed sensors. And and why is that? It's because they can take advantage of the existing transportation infrastructures. And then we will move to the next part of the presentation, let's say the second part, which is the wireless sensing technology. And we will see that here it's probably more appropriate for local monitoring, so a specific landslide, not a complete infrastructure. And the good thing, the interesting thing is that it's totally, it has very low environmental impact. And of course, I will not end my presentation without the conclusions. Okay, so let's start. And let's talk first about optical fiber sensing. And when we talk about optical fiber sensing and distributed sensing, very often we are talking about transportation infrastructures. So transportation infrastructures are pipeline, highways, railways, power lines and cables, waterways, any linear long distance structure that is used for basically communication of people, product, energy, and so on. It's very common to have along this, provided that they are not too old, and it's very common to have optical fibers laid along these transportation infrastructures, because the optical fibers are used for communication. And well, they are also kind of linear infrastructure. So it's kind of matching between the two approaches. Communication. So people are using the optical fiber for their own communication, like a pipeline operator who use it for its internal communication, and also for its SCADA. But some of them are also using the optical fibers to lease this optical fiber. We could talk about dark fibers. So they are, let's say, making money also not only with transportation of the natural gas, for instance, but they are also making money with by leasing the optical fibers for bandwidth increase. The interesting thing is that if we know about the physics in optical fibers, it's possible to turn them into strain, temperature, and vibration sensors. And what is even more interesting is that you can make the sensors continuous. So that's why we talk about distributed measurement or distributed sensing, meaning that we have along the optical fiber thousands or hundreds of thousands of microphones, temperature, thermocouples, and strain gauges. I'm just an image, just to picture a little bit what I'm talking about. But it's really like having multiple sensor or a sensor every 1 meter, but it's not a physical sensor attached to the fiber. No, it's the fiber itself that is the sensor. And then if we talk about wireless sensing, what is interesting is that you can have that kind of sensor laid in a landslide, because we cannot cover thousands of kilometers or hundreds of kilometers with that technology, but it can be a support of the optical fiber sensing technology to, let's say, focus specifically on a landslide threatening a pipeline or a highway. And that kind of sensor can be implemented, or let's say the radio communication used in wireless sensing can be used to connect strain gauges, inclinometers, piezometers, and seismic sensors. What we will focus on here is on seismic sensors. So let's start by with optical fibers, and I cannot resist the pleasure of talking about physics. Being a physicist myself, I'm not a geotechnical engineer nor a geophysicist. I'm pure physicist with an optical fiber and optical sensing background. And let's say, if we talk about optical fibers, and the physical mechanism that's behind sensing is light scattering, and light scattering is natural. As soon as you have light, as soon as you have a medium, you will have scattering. There is no way to avoid it. And actually, light scattering for telecommunication is an impairment. But for sensing people, it's a very good friend. We will see why. And scattering, as I said, is natural because it comes from the inhomogeneities in silica, which can be static or dynamic, moving or vibrating. So, and scattering, as I said, is natural. So here is an example of a glass rod where we have a laser beam propagating. You can materialize the laser beam because you have scattering. You have a change in the density of the media. You have a more dense media, and then more scattering centers, and that provokes the scattering. So you can see the beam because you have a fraction of the light that is taken out from the propagation. And that's what we take advantage of in optical fiber sensing. So that kind of approach, that kind of physics is implemented in a technology called optical time domain reflectometer, where a pulse is launched into a fiber, and all along the fiber you have a fraction of the light that is scattered. And even a smaller fraction of that light is back scattered. So it goes in all directions, and a fraction of it is coming back. It's back scattered. So it's like a continuous reflection. So the signal is recorded by a detector, and we have a signal, and that is measuring, or an interrogator that is measuring a trace, which is a function of time, the time of flight of the pulse in the fiber. And we can convert the time of flight of the propagation into distance, so that we can locate events. We can tell where things are happening. Then, by analyzing the scattered light, we see that its spectrum is not just a single light component. It's not purely monochromatic. If we send a pulse, a monochromatic pulse, it will be scattered with several components. We have one component called relay, which is at the same wavelength as the input signal and as the input pulse. And then we have side peaks, which come from various origin. I'm not going to detail that here, but one is called Brillouin and the other one is Raman. And nature is beautiful because each of them has a potential application for sensing. So with relay, you can implement what we call a distributed acoustic system, or let's say a dynamic strain sensor. So we will capture changes in the amplitude and the phase of the signal, fast changes, and then we can then have a kind of vibration sensor. Raman, the intensity of the Raman lines is sensitive to temperature. So by measuring the amplitude variation, we have an information about the temperature of the fiber at that specific location. And the Brillouin line is also very interesting because it has a cross sensitivity to strain and temperature. But here we don't look at the amplitude variation, but we look at the change in the wavelength. And that change in wavelength is proportional to temperature and strain. Actually, it's the optical frequency, not the wavelength. So we have three techniques that can be used for fiber sensing. The only, let's say, the negative point, let's say, is that we cannot have just one unit, one interrogator that does everything, because the type of signal requires a very distinct optoelectronic to create the pulse, to generate the scattering, and to analyze the scattering, the light that's coming back. So we need three boxes, three interrogators. Now, from temperature and strain and dynamic strain measurement, we can extract interesting things. First, with strain measurement in the soil, we can measure or we can monitor subsidence and landslide. And using temperature, we can actually monitor erosion and eventually calculate what is the depth of cover. So what is the remaining soil, quantity of soil or depth that we have, the remaining quantity of soil that we have on top of the fiber. For strain sensing, we need a dedicated strain sensing fiber or cable. Eventually, we can imagine to have embedded in a communication cable strain sensing elements. Now, for optical fiber, for temperature, we can use a common optical fiber communication cable. And that kind of technology has been implemented in, several projects for now more than 15 years. And here is an example. It's a landslide that was detected in 2011 in Peru on the PLNG transport system. So it's natural gas transport system. And that's we could associate with that landslide two patterns. One spatial pattern, which is the strain versus distance, where we see the pattern developing over time. It increases, the intensity increases, and we also have an information about the width of the event. So we have information about the spatial extension of the landslide. Here we are talking about 35 meters. And on the top right figure graph, we have the temporal evolution of the peak value and let's say the neighboring let's say at rest section of the fiber. And so we can also monitor the velocity and how fast this landslide is developing. And that's captured and collected over time and sent to a server that can do analysis and generate alarm if it's let's say if it's configured for such functionality. Now, using let's say dynamic strain monitoring, we can do, let's say, for instance, rockfall and avalanche detection. Here is an example where we did a trial that's in Switzerland, and we laid an optical fiber cable in the ground. It was buried as well, and we were measuring back and forth, so the fiber is looped back, and we generated an explosion nearby the cable, and we could capture two signatures, each of them corresponding at two different positions in the cable. And if we look at the specific position where we have the maximum intensity, and we see the waveform associated with the explosion. So we have like a damped harmonic oscillator curve showing the time evolution of the vibration and its attenuation after a certain time. So, for instance, that has a very let's say interesting application to detect rock falls on a highway or on a railway. If let's say if optical fibers, of course, are laid in parallel to the structure, which is kind of for railways kind of very common, at least in Europe. Now, with an example here is, or two examples with the application of temperature sensing. So we see an example on the left of erosion that occurred after a heavy rainfall. So the soil was excavated by the water flowing, and we could see in the temporal pattern a drop in temperature and then a return to the ambient temperature in the ground. And that event has as well a spatial extension, as we can see, of a few meters. So as in the other two examples, we see that we can have an information on the position of the event and on the severity and on how it has evolved over time. On the right figure, on the right graphs, what we have here is another example that's again in Peru, and what we see is in the spatial pattern we see three events with varying amplitude, time varying amplitude, that are kind of with distinct maximum. And if we look specifically to event one and compare the peak amplitude with the ambient temperature variation, we see that we have the same pattern. We have a 24 hours periodicity. So, but the difference here is that the amplitude is much lower, and also we have a phase difference, so a time delay. And actually, that's because here the fiber is not directly exposed, but it's still buried, but with less material on top of it. And by calculation, we can find that actually for that specific event, we have, so event one, we have, let's say, still like 10 to 15 centimeters on top of the cable. And the last one, what was remaining was 50 centimeters. And for event two, it was about 20, 25. So we have a technique here that can also detect the preliminary signs of a risk of exposure of the cable. And if we have a pipeline, then exposure of the pipeline. And of course, in any case, if we are along a highway or railway, it's also an indication of, let's say, a reduction of the material on top of the fiber, which can affect, of course, the infrastructure. Okay, so that's all about examples, all about distributed sensing and detection of natural hazards, and even, of course, landslide. So let's now move to the example of wireless sensing. And in this case, we are talking about a network of wireless sensors, which are actually accelerometers, and that has also a temperature sensor embedded. We can implement about 50 of them, and they communicate with a gateway. We can also use the same communication module, radio communication module, to connect piezometers, inclinometers, well, just any kind of geotechnical type of sensor. And that data can be also collected by the the gateway. We can also have data coming from third party directly on the gateway, like from via Modbus from the SCADA, and this information are, let's say, transferred to the cloud, where we can do, let's say, create digital twins of the event we want to monitor. And we can also combine by opening via API, we can open door and synchronize database, collect data from also third party, like meteorological data, any kind of information that can be useful for modeling. And then depending on the type of event, we can create KPIs that will be that we will be using in a dashboard that can be where we can generate alarms. So this is, let's say, a bit the architecture that can be implemented. And as I said, here we have sensors that are synchronized. That's very important for seismic monitoring. Here is an example of an active seismic monitoring test we did. So we had a person hitting the ground with a hammer, hammering the ground, and what we see, each line corresponds to one impact. If we zoom in the impact, so just one impact, we see that it has a waveform. So it's a structure like the one we saw with the optical fiber. It's characterized by a period and a decay rate. So we can calculate this information and actually relate them to the spectrum of the complete trace here, and we see that actually the value that we get corresponds for the maximum correspond to the period here, and for the decay rate to the amplitude, and it's just the inverse of the time parameter. And then we also have a second line, which is which is an harmonic of the central component. So we can do soil characterization and active seismic monitoring with that kind of sensors. Now there are other techniques that are using passive seismic monitoring, and for instance, provided that we have structures that are rigid, like rock pillars, or eventually bridges, tunnels, dams, concrete dams. And we can do a model analysis and also extract information about the natural frequencies. And from this information, we can it's possible to monitoring the change in the natural frequencies and the structure of the model, and the model structure, that there is a degradation in the structure. Now, if we are willing to monitor a landslide, because the structure, the material is more loose, then we will need to do seismic velocity analysis. But in any case, the idea here is to capture just ambient noise to monitor change in the structure of the object we are monitoring. And what is required is to have multiple sensors and being able to do synchronized captures. We need to have very low frequency capabilities, and basically 0.1 hertz is probably even not good enough. So, and we can go below 0.1 hertz. And of course, because we are talking about noise and capturing noise, generate ambient noise, we need very sensitive sensors. Now, here is an example of a work we started recently on a water reservoir in Sao Paulo, area in Brazil. And we can see the capture. So we have implemented 7 sensors in the slope of the embankment on the top and some sensor at the bottom. And we were capturing events that are related to, let's say, cars passing by and, well, any source of noise in the area to perform this natural frequency monitoring. And a last example that is probably the most interesting of this presentation is the monitoring of a landslide in Switzerland. So they implemented in that specific landslide that was threatening a road here at the bottom. So they were monitoring the landslide using various conventional instrumentation, static instrumentation, doing electric profiling, using inclinometers, and also they were monitoring the ambient noise caused by the cars passing by. And they were doing that by using 2 seismic sensors that were located in the stable part of the landslide, so on the site. And they were, well, the distance between the 2 sensors is, if I remember correctly, 10 meters, about 10 meters, maybe a bit more. And in that specific case, capturing the passive seismic noise, they were cross-correlating the information between the two sensors, the waveform of the 2 sensors, and comparing the cross-correlation with a reference value. They were extracting the relative velocity variation, so normalized. And then we can see over time that while it's fairly stable until let's say end of July and in 2010, then they had a drop because it was associated, or at that specific day they had a very heavy rainfall, and then the relative velocity started to drop a little bit more. It was not as stable as before until it reaches a point where we had a very significant variation, decrease of about 7%. That was mid-August, and that was, let's say, associated with another heavy rainfall. And then a few days later, the slope collapsed. So they were using that kind of approach, so passive seismic interferometry, to extract, to evidence or to predict, let's say, well, the occurrence of a landslide. Well, prediction is probably not the right word, but let's say to detect the preliminary signs or signature, the preliminary signature of the event. Okay, so that last slide will leads us to the conclusion. So as I stated at the beginning of the presentation, this is really a discussion about some cases and how to, and we see that we have 2 complementary approaches. Optical fibers, you can use them if you have an existing infrastructure. It's fairly simple. You just connect the right interrogator, you monitor temperature, strain, vibration, and then the connection is kind of a retrofit with very limited environmental impact. There is little excavation to be conducted, so just connect the equipment in a shelter and usually you have shelters for communication equipments. If you really want to have very accurate strain measurement, you may have to do some excavation. but you can take advantage of remediation work to install that specific cable and splice it to the communication cable. And the advantage is that when the equipment is connected, you can hook it to the communication network and take the data and do the analysis and eventually generate alarms when it's configured for such application. And really, we get a system that is monitoring permanently the infrastructure and detecting events that can threaten the infrastructure. The advantage, then if we want to have a more detailed, we understand better how a specific section of the infrastructure is let's say moving, we can do, let's say, more traditional implementation, so to monitor specifically the landslide. But again, if we use wireless sensing, we don't have to excavate for the cabling. We have batteries, wireless sensors with batteries. So then the sensors can be so that the implementation, the installation would have also a very limited environmental impact. You don't disturb the landslide too much. And for the data communication, eventually, if there is no optical fiber available or a terminal equipment where you can hook the gateway, you can communicate via 3G, 4G, or eventually satellite data communication network. And some of my partners, they use Starlink just to communicate the data. And of course, well, I have been talking a little bit more about the dynamic monitoring and the seismic monitoring, but you can, of course, use static devices such as inclinometers, piezometers, tilt meters, well, whatever you need to, whatever parameter you need to monitor. So, ladies and gentlemen, I'd like to thank you very much for your attention. I also would like to thank again Lancient and Roberto for putting together this event. And if you want to learn more and read more about what have been talking about, there are some of these references are kind of comprehensive and well detailed. So just feel free, and of course I'm available for questions. Thank you very much.